Hey guys, welcome back to the channel. In this video I'm going to be going over topic 9.1 IB Chemistry, Oxidation and Reduction. Oxidation and reduction are widely used topics and they'll come into play in many other topics of IB Chemistry, just like topic 8 and topic 10, just off the top of my head, but also in your other subjects such as IB Biology. I study biology and this has come up quite often. So this will be a topic you'll have to pay quite a lot of attention to, and after a while it will seem quite easy. So I'll be doing this under 10 minutes. So with oxidation and reduction, we call it redox. That's a portmanteau, a combination of two different words. With redox reactions, the main focus is electrons. And so oxidation and reduction are to do with electrons. Oxidation is the loss of electrons, reduction is gain of electrons. These definitions here, this definition for reduction here might seem a bit counterintuitive, but you're going to have to know it, and after a while it will get easier. Oxidation is the gain of oxygen as well, as the name might suggest, and reduction is also the loss of oxygen. Oxidation is also loss of hydrogen, and reduction is the gain of hydrogen. And also, if you guys notice here, hydrogen and oxygen, the reason I put these together is due to their electronegativities. And if someone can actually comment down below and explain what it is to do with the electronegativities, and if they're right, I'll give them a special shout out in the next video. Next, you need to know what oxidizing agents and reducing agents are. So an oxidizing agent is something that will oxidize something else. You can think of agents like in movies, like Agent 007, James Bond. He does something. So an oxidizing agent will oxidize something. So in itself, it'll have to be reduced, right? It'll be reduced in itself. Similarly, a reducing agent will reduce something and it would be oxidized. So as you can guess, for redox reactions to happen, if oxidation happens, reduction must happen, and if reduction happens, oxidization must happen, vice versa. The discussion is this thing called the reactivity series of metals, which is basically a ranking of all the metals based on their reactivity and specifically their ability to oxidize something. So metals normally form positive ions, so they're going to be losing electrons, so they're going to be reducing agents, because they themselves get oxidized and lose electrons, which is why metals are positive ions in the end. So the highest reactive or the strongest reducing agents, or most easily oxidized, are going to be the ones at the top. So the higher, the stronger the metal. So with this helps us predict how reactions will occur. So if we have potassium being added to, say, sodium plus, then what would happen is we'll get K plus and sodium by itself, because potassium is a stronger reducing agent. Reducing agent than sodium. Sodium's gonna gain electrons, and potassium's gonna lose electrons, because potassium has a greater tendency to lose electrons because it's higher up in the reactivity series. It's all to do with electronegativities, and if someone can explain that in the comments, they'll get a shout out as well. Alright, so another important thing to discuss is something called the Winkler Method, which is to do with measuring the pollution levels of water by considering how much organic material is in the water itself. So Winkler Method measures the level of pollution and the amount of life in water by measuring something called the Biochemical Oxygen Demand, or the BOD. So BOD is basically the amount of oxygen that's demanded by a particular amount of water and the organisms that live there. Okay, so oxygen is needed for aerobic respiration, and because of that it can be a good measure of how much life is there. So what we first have to do is we have to quantify the amount of oxygen there is, and we do that by trapping the oxygen in manganese. So we have manganese sulfate, and we add that compound in excess to water. So notice how there's OH minus ions in the water, and this is all aqueous, and you have gaseous oxygen. This is all in the water. What happens is this SO4 actually dissociates, and we have an Mn2 plus aqueous ion. And what that does is it combines with the oxygen, and it forms manganese dioxide as a solid precipitate, and it can be used in further analysis. So this manganese dioxide can also be combined with actual iodine ions. So iodide ions, are oxidized to form iodine gas, right? So when we have the oxidation of iodine, what will happen is something else will be reduced. right? So what's being reduced here is going to be manganese. So sorry, it's not the manganese that reduced. Manganese is oxidized. What happens is the hydrogens are going to be. So you know what? I don't think I should explain that part. I think perhaps because it's not in the syllabus. Let me just check quickly. Give me 2 seconds. No, you don't have to know that. So first, you just need to know this equation, and you don't have to identify which one's the oxidizing agent, which one's the reducing agent. But so manganese dioxide has that initial oxygen, right? And what happens is that oxygen reacts with these iodide ions, and we get manganese 2+, right? And we also get this iodine aqueous compound. So aqueous iodine can be used in our next step, which is aqueous iodine being titrated against with sodium thiosulfate. Sodium thiosulfate is quite a popular molecule to work with, and you've probably done practicals with it in the lab. And what it has is this 2- anion called the thiosulfate ion, which combines with the iodine aqueous, and we get 2 iodine ions, and also we get these S4O6 2- aqueous ions. And so because of this, we can use this ratio of the oxygen ions initially to, number of oxygen initially to the amount that we needed to titrate, the amount of sodium thiosulfate we needed to titrate it against, and we can work out how much was initially there. So it's working backwards. We have this, we are going backwards. So with the Winkler method, it can be really complicated to understand. So what I've done for you guys is extracted the information that you're going to need for most of the questions you're going to do. So the most of the questions of Winkler method will involve calculations more than really writing out all the equations. So what I did was I wrote out the ratios of the ions. So as I said, you're going to work from the final titration of sodium thiosulfate, what the oxygen was. So the ratio of thiosulfate ion to aqueous iodine is a 2-to-1 ratio. And from the previous step, the ratio of aqueous iodine to the ratio of manganese dioxide is 1-to-1. And the ratio from the previous equation, even before that, the ratio of manganese dioxide to oxygen dissolved is going to be 2-to-1. So if I recommend you guys draw out this exactly as it is. Sorry, this is a bit to the left. And what that will do is get you in the habit of thinking about this logically, and what you'll work out is that the final ratio of the titration that's important is that there'll be 4 thiosulfate ions for every dissolved oxygen molecule. So again, we need to work this out. So if we get 1 mole of thiosulfate ion used, that means we have 0.25 moles of oxygen in the water. So that's how you use the Winkler method for calculations. Next, we need to talk about oxidation states and oxidation numbers. So this is not to do with the oxidations of in terms of redox, but more so charges. So the oxidation state of a substance or a species is the charge that something would have if its bonds were purely ionic. So if we have H2O, if this is covalent bonding, but if it was ionic, then the oxygen would gain 2 electrons and be 2 negative, and each hydrogen would be +1, right? 1+, and it would be that would be the charge of each of these. And is that it? No, I'm just kidding. That's wrong. We can't write oxidation states like that. Oxidation states actually are kind of weird, because normally for ions you write the number followed by the charge, but for oxidation states it's backwards. Well, the proper way actually, well, the normal way. So oxidation state would be with the sign first and then number after, right? It'll be like that. Each hydrogen here has +1 charge, each oxygen has -2 charge, and the overall charge is going to be 0. Same with, let's say, manganese dioxide. Manganese has a +4 charge, right? And then oxygen has a -2 charge. And because of this, 2 times the -2 is -4, plus the +4 gives us 0. And oxidation numbers are this other thing. So oxidation numbers are to do with the more with metals, where if you've probably seen this iron 3. It's just in brackets, so that just means that it's going to be iron 3+, iron 2+, etc. Make sure you guys write out oxidation states so that you can figure out which species is going to be reduced or oxidized in a reaction. And using the previous definitions, work out which one is the oxidizing agent, which is reduced, and the reducing agent, which is oxidized. Other than that, guys, that's the end of the video. Hope you guys enjoyed. See you later. Leave a like and make sure you answer the comments. Answer those questions I mentioned in the comments if you guys want to get a shout out, or just a thumbs up. It'll be nice to show you. See you guys later.